Okay, tonight we're going to discuss chi-square, relative risk, and odds ratio. And that is something that involves categorical data. For instance, let's say that you know that you have a population, has some smokers in it, has smokers and non-smokers in it. And you want to know, for instance, what's the likelihood, is there an association between smoking and psoriasis, let's say, for argument's sake. I don't like psoriasis. I'll have to go back to something a little bit more common, reasonably a little bit more common. Persistent cough. Okay, let's say persistent cough, right? Association between smoking and a persistent cough. A lot of people have persistent cough, even people who are not smokers, right? For one reason or another, allergies or whatever. Okay, so let's examine this. I'm going to say that we go out and we randomly sample 200 people, right? But we kind of like, we get we're a little bit more careful. We randomly, out those 200 people, actually, there's 100 smokers that we randomly sample. In other words, we pick all the people, we get a list of all the people who are smokers, we randomly sample 100 people from the smokers, and we randomly sample 100 people that are non-smokers. Okay, and I take all those 200 people together, and it turns out that there are 50 people in these, out of those 200 people, that have a chronic cough, right? So what's the probability in this population? In other words, the prevalence of chronic cough in this population? 50 out of 200. What's the prevalence? Somebody? Right? Prevalence is just how many people, percentage of people have, 0.25. Right? 25% of people in this sample that's representative of, presumably representative of population. 25% of the people in this population have a persistent cough. Okay, so now I'm going to set up what we call a contingency table. This is going to look at least vaguely familiar to you. It's a 2x2 table. Looks very much like the table that we used when we were working with diagnostic tests. Now, as a convenience, I'm going to try and do something that I like to keep consistent, the way I lay out this table. In the rows, I like to put the exposure, right? The element that I think is causing a disease or a symptom or a reaction or something like that. And in this case, what would be the exposure? Is it smoking or coughing? Smoking's the exposure, right? I like to put a positive for the exposure, smokers, people who smoke, on the top row, and non-smokers on the bottom row. Do you have to do it this way? Absolutely not. Will this make it a little easier for you? I think so. I think there's reasons why this may be more convenient for you than doing it the other, like putting the others in columns or reversing, putting non-smokers on top, smokers on the bottom. It's just a convenient way to do it. A lot of textbooks lay it out that way. A lot of software produces output that way, and so on. Okay, now that leaves the columns. The columns are my disease, right? I'm going to do the same thing. In the left column, I'm going to put coughers, have a cough, and no cough. Everybody fits into that one of these boxes out of the 200 people, right? They either don't have a cough, don't smoke, or they have a cough and smoke, or they don't have a cough and smoke, or I forget. I've lost track. I can't do it anymore. Okay, so how many smokers did we say we had? We had 100 smokers, right? And we had 100 non-smokers. Okay, now let's assume, we always assume that there's no difference for the start. We love our null hypothesis. Our null hypothesis is always our starting point. Let's assume there's no difference between smokers and non-smokers. Out of those 100 smokers, how many people with a cough would we expect to get out of those 100? What's the prevalence? 25%. So we'd expect 25 smokers. How many people would we expect not to have a cough? 75, right? Like there's 100 people altogether. Okay, how about non-smokers? Since overall the population has 25% of smokers, and I'm starting with the assumption there's no difference between smokers and non-smokers, how many non-smokers would we expect to have a cough? 25, no difference, right? Okay, this is what we call our expected values. If there's no association between smoking and non-smoking, this is what we would expect to see. Okay. Now, let's say we really do this study. And in fact, we find out when we do this study, the box, as it turns out, doesn't quite look like that. Maybe it looks something like this. Well, actually, I'm going to start out with it looking like that. 25, 75, 25, 75. Okay, smokers, non-smokers, cough, no cough. Okay, I do the study and I get exactly the same result as I would have expected. What does that tell you? It tells you smoking doesn't cause coughing, right? Not associated with coughing. These are my actual counts or my actual values, right? Or sometimes you might call them your observed values. That's another way to phrase it. Okay, not very likely, is it? Okay, let's say I want to put together an estimate of how different is my expected values from my observed values. Okay, well, if I did it here, I would say, well, smokers, how many people were smokers and had coughs? 25. When I observed it, 25. Same number. There's zero difference between the two. How about this box and this box? Zero difference between the two. How about this box and this box? Zero difference between the two. How about this box and this box? Zero difference between the two. There's no difference between any of the boxes. So if I added up all the differences, they all come out to zero. Zero, zero, zero plus zero plus zero plus zero. The differences between what I expected and what I actually saw is zero, right? Well, that's not very informative, is it? Even if that were true, even if this assumption as to what our expected values is true, the likelihood that we get exactly 25 and 25 and 75 and 75, not very likely, right? You'd expect a little bit of variability, right? Because just because by chance you pick out 100 smokers randomly, even if it's 25% of them have a cough, you don't expect to get exactly 25. Sometimes you may get 24, sometimes you may get 28, sometimes you get 20. You just expect some variability. So you do expect there to be some difference. Let's say, as it turns out, the difference is 27, and that would make this 73. And this was 20, and that would make this 80.
Okay.
Yes.
For that first observed case too, you just made that assumption that it's the same too. You just assume that the observed is going to be exactly the same, right? I mean, you're expecting, there's no difference than the observed. There's no difference, but you just assume that the observed was ideal, right?
Right.
Okay.
Yes, that was exactly the same, that there was no difference, that really smoking did everything, and we got really lucky. Okay, now this might be a real case. This might be really happening. Now, there is a little bit of a difference between smokers and non-smokers in this instance. Not a lot. I mean, it could have been, like that 25% of non-smokers had a cough, but it just happens that out of the 100 that we picked, we only got 20 this time, right? Because we sampled randomly, right? But it still could be 25%. Okay, could be that 25% of the smokers had a cough. 25% of smokers in the population had a cough, but we took 100 of them randomly, and it turns out we picked 27. That could happen even if there's 25%. So not much difference here. Okay, so now when I go back cell by cell and I look at the difference between my expected values and my observed values, one of the ways that I may quantify the difference is do the same thing I did before. Check each box against the other and see what the difference is. Okay, so I'm going to take where's my pen there? I'm going to take my observed values minus my expected values. Okay, and I'm going to make a chart here, right? An informal chart here. Okay, so my observed value is 27 for this box. Up here is 25. So 27 minus 25 is 2, minus 2, right? 20 minus 25 is, I keep doing this backwards. Observed minus expected is plus 2. Observed minus expected for this box is 20 minus 25 is minus 5. Observed 73 minus 75 is minus 2. And 80 minus 75 is plus 5. Okay, those are my, if I add all my differences together to see how big the difference is, what do I wind up with? 0 again. Don't help me, it does it. There's a couple of things I could do at this stage to combine these differences so I can get an overall difference for how different the observed values are from the expected values. One of them is just work with the absolute values. In other words, ignore the signs, just go more positive, right? That's one thing I could do. We don't usually do that in statistics. You've seen us, in order to rectify this, most of the time we've squared the quantity. Remember when we did some squares, we squared the quantities? Okay, so I'm going to, instead of this, I'm going to square each one of these quantities. So for this box, 2 times 2 is 4. For this box, 2 times 2, negative 2 times negative 2 is plus 4. Negative 5 times negative 5 is plus 25. Plus 5 times plus 5 is plus 25. So if I add up all these differences, the total is 58. Right? 58. So now I got a problem here. And my problem is that two things have happened here. I got a number, I don't really know what it means. Right? And not only that, but it's kind of like been blown up because we made it a much bigger number by squaring everything. So it's kind of out of the realm of what we normally deal with, right? So I'm going to have to do something with that. I'm going to do something with that later on. I'm not going to do it right now. But now we got a number 58. Whoops. We got a number 58. Ah. Okay. Here's our number 58. Now, let's say that there's no association between smoking and a chronic cough. Okay, if that's the case, we would expect the values in our observed values to be similar to the values in our expected values, right? They'd be similar. Would we expect them to be exactly the same? No, because that's, it's a sampling process. There's some probability, some chance involved in this when we sample, right? But we would expect that the difference would be a small number, right? If there is a difference between smokers and non-smokers, then the differences you would expect the differences between the observed values and the expected values to be what? Bigger or smaller? Bigger. You'd expect bigger differences, right? And you say to yourself, the bigger the difference is between these numbers, the more confident I am that there really is a difference between smokers and non-smokers. So what we're looking for is how big is that number when we add up all the differences. If we get a really big number, we have a lot of confidence that we can say that there is an association between smoking and non-smoking. In other words, reject our null hypothesis that the expected values and the observed values are the same, right? That there's no association, right? And we can reject that and say there is a difference because look how big the differences are. They weren't likely to be due to chance. Okay, so now we're going to formalize this a little bit. And the way we're going to formalize this is we're going to calculate the value, the statistical value that we call chi-square. It's no more complicated than what I've already done here. I'm going to start on another page, so we'll use the same numbers. I'll make up a new number for the observed values. Let me get this out of the way. Okay, here's my 2x2 table. Okay, and this is smokers, non-smokers, cough, no cough. Okay, 100, 100, 25, 75, 25, 75. What table is this again? Those are my expected values. Okay, let's say my observed values turned out to be, let's see, smokers, maybe we got 35, and that would leave how many people? 65 that are don't have a cough, no cough, and smoker, and non-smoker, and maybe for non-smokers we got 15, and we got 85, right? Total of 100 in both cases. Okay, notice how many people with costs we got. Got 50, just like we predicted in our expected values, right? Okay, so now let's take a look at a value that we can use, a statistic that we can use to estimate how big this difference really is between expected and observed value. And we're going to call that value chi-square. Okay? Hey, what's chi-square look like? Chi-square is like a big X. Right? Chi is like a big X. Like big X. Chi-squared. So we're going to use that symbol for it. What's chi-square going to be equal to? Chi-square is going to be equal to the sum of the observed values minus the expected values squared over the expected values. Now, I'm having a senior moment here. Somebody just check that formula in the, that's not, yeah, I'm sure that's what it is. Don't check, you don't check it. I'm sure that's it. I hope. Okay, never mind. You know, sometimes you write something and you look at it and you're not sure it's right. So what do I mean the sum of? The sum of all four boxes, n is equal to 1 to 4, you know, whatever I want to represent the box with that. In this case, it's four boxes. You could actually have a bigger contingency table that could have 2 rows and 3 columns, 6 boxes, or 3 rows and 5 columns, right, and so on and so forth. It's possible to do that. For now, we're just going to work with 2 by 2 table. So I'm going to calculate this now. I'm going to calculate that value for each one of these boxes. And what is it? Observed value, observed minus expected, squared over the expected value. We know why we did the square, right? Why am I dividing by the expected value? Right? Well, it's going to counteract the square. It's going to bring it back down into the range that we would expect. You know, like in other words, it's kind of the way with when we did the square root at the end of the sum of squares. You know, when we started working with variability, the variance, and standard deviation to bring it back down into the range of numbers that we normally would work with, that we're normally working with. So, what is chi-square equal to in this case? Chi-square is equal to, well, for the first one, it's going to be observed. This is our observed value. It's going to be 35 minus 25, right, squared over, what was our expected value? 25. Plus, the next box is going to be 65 minus 75 over 75. Plus, let's see, which I guess.
That's squared also.
That's squared also. They're all squared. Plus 15 minus 25 squared over the expected values is 25 plus 85 minus 75 over the expected value of 75, right? And that's squared also. Okay, so let's see what I got here. 35 minus 25 is 10. Squared is 100 over 25. That's 4. Plus 65 minus 75, that's 10. Squared is 100 divided by 75. 100 divided by 75 is 1.33. Right? Everybody agree with me so far? 15 minus 25 is 10. Squared is 100 divided by 25 is 4. 4 again, plus 4. And finally, 85 minus 75 is 10. Squared is 100 divided by 75 is, again, 1.23. So what is our chi-square value? It's 8, 10, 10.67. That's our chi-square value, right? Pretty simple calculation. There were a couple of questions because there was something that came up called the Yates Correction factor. Okay? For the moment, don't worry about the Yates Correction factor. What the Yates Correction factor would have us do, see where it says 35 minus 25, and you get 10, right? It would have us subtract 0.5 from that value. So when we square it, it's a smaller number. That is in there because 2 by 2 tables tend to overestimate or overly generous with the chi-square value. But we're not going to worry about that, especially if we have a decent sample size, right? Which would be, we want to make sure the expected values are always above 5 for any of these. If the expected values are less than 5, then we got a problem with our sample size. Okay, so chi-square is equal to 10.7. So now I need to understand what's the likelihood of getting that big a difference if there is an association or if there is not an association. So our null hypothesis is H null is that there's no association, right? And our alternative hypothesis is that there is an association, that smoking affects the amount of cough, whether or not you have a that you have a chronic cough. Okay, so now how are we going to demonstrate? How are we going to demonstrate that there's a big enough difference between expected and observed values using this number called chi-square? Well, the way we're going to do that is there is a chi-square distribution. Okay, and it's a graph. We're going to take a look at, just like there's a normal distribution, there's a chi-square distribution. And I'm going to see if I can't find it here and blow it up. I think this might be it. No, it's not it. Chi-square. Here we go. I think that's it. Okay. Okay, here's chi-square distribution. Okay, so now, unfortunately, they really get a little bit overboard here in the how they lay. I'm gonna draw this slightly differently. Okay, so now imagine that this I can't draw it here. Let me go back to my notepad. I don't like that particular drawing. Okay, here is a graph of probabilities, right? This is chi-square down here. This is the probability, the probability of an outcome. Okay, so now what's the probability of getting 0 if we did a study like this with 100 people on each group? What's the probability of getting exactly what's the expected value? It's not very hard, right? I mean, it's going to happen occasionally. It's kind of like flipping 100 coins and getting exactly 50 heads. It's going to happen, right? It's the most likely single outcome, but it may only happen 10% of the time or 5% of the time or something like that. But still, it's most likely outcome. So the graph is going to start here. The likelihood is that we're going to get a small difference, a small chi-square difference between the two of them. But then eventually, as that chi-square gets bigger and bigger, it's eventually going to start to get less and less likely that there will be no association between the two of these. So the chi-square starts to look something like this, right, with the probability going down here. So this represents the probability of getting a chi-square value within, what's the probability of getting chi-square value if there's no difference between the estimate, the expected values and the observed values. Okay, so now if chi-square is 1, right? Well, the probability of rejecting the null hypothesis and being wrong is pretty big. It's this over here, because this is the probability that you would have a chi-square bigger than 1 when there's no association, right? But if you go way down here, you can get to a point where there's only a 5% chance that we would get that big a chi-square if there's no association between smoking and cough, right? That's the probability of rejecting the null hypothesis incorrectly. In other words, the further we are out here, the less likely we are to make an alpha error if we reject the null hypothesis. That's our p-value, exactly right. And what do we want to, usually alpha is equal to 5% chance of being wrong, right? Alpha error, right? So we want our p-value to be less than 5%. So you got to be this far out. There's a different chi-square distribution for the number of degrees of freedom in your table. Okay, this is a chi-square table, right, for our particular situation. Okay, how do you calculate degrees of freedom? Degrees of freedom is equal to the number of rows, number of rows minus 1 times the number of columns minus 1. Okay, how many degrees of freedom do we have? 1. 1 times 1, right? Degrees of freedom is 1. So this is appropriate for 1 degree of freedom. Okay, as it happens, this value here, you probably heard it in the lecture. We'll actually go online and we'll find a table. This value is 3.84. The probability of being wrong if you reject the null hypothesis, if you have a chi-square value of 3.84, is less than 5%. So what would you call that value of chi-square for our study that's going to determine whether you can reject or not reject? How about a name like critical value for chi-square? We got a chi-square of how big? 12. We're all the way out here, right? Our chi-square is out here. There might only be a 1% chance of getting that big a chi-square and not having an association and having the difference be due to chance in the observed and expected contingency tables. Okay, so what would we do? Would we reject our null hypothesis or fail to reject our null hypothesis? Since we got a 12, a 10, we reject it, right? Because it's very unlikely that we would get that big a chi-square value if there's no association between smoking and non-smoking, right? We wouldn't expect to see the differences that big by chance in those boxes. Not so hard, right? Right, for 1 degree of freedom. In fact, let's look up a chi-square table. Let's see if I can't find another one here. Now it's a different number for different degrees of freedom. I can't find it. Chi-square. Let's see what this is. Nope, that's not what I want. Chi-square. Let's see PDF. Let's see what that does. Yeah. Grab table. Okay, here's a summary of the table. It's a little faded, it's a little hard to read. Okay, if you have 1 degree of freedom, area to the right of the critical value, 5%, 5% chance of being wrong, is 3.84, right? If you are at 6, you're down to 1% chance of being wrong. So we're all the way over here at 10, or even less than 1% chance of being wrong. If our alpha were 10% instead of 5%, we would reject if the chi-square value was bigger than 2.7. Right? So this table, and now if we had a 2 by 3 table, that would be 3 minus 1 is 2 times 1 minus 2 minus 1 is 1, 2 times, there's going to be 2 degrees of freedom. So our alpha, our chi-square that we would need to exceed would be 5.99, right? And we would expect that because there's more boxes, there's more differences. So we would expect it to be a bigger number, right? We're adding up each of those results of that observed minus expected divided by expected. Okay. Yes.
So basically, in simplest terms, you can think of it as long as chi-square is bigger than the critical value, then you're rejecting the null hypothesis.
Exactly. And if it's smaller than the critical value, what does that tell you? That tells you the difference between your observed values and your expected values is not very great. So there's no reason to, think it's not due to chance, the differences, rather than, smoking causing people to cough more. Okay, does that make sense to you guys? Anybody have a problem with that? Does it seem like an incredibly hard calculation? Not really, right? It's pretty simple. It's pretty simple statistic, right? Now there is an issue with this idea of the Yates correction, and the reason for the Yates correction is because, let's say that the real rate of prevalence of coughing in this population was I call it 25. Let's say it was 25.5%, not 25%. Well, these are whole, when you build these tables, they're whole numbers, right? In other words, the actual prevalence is continuous. Could be 25.3, 30%, 31.2%, right? It's a continuous number. But the values that you can have in here are going to be integers, going to be whole numbers, right? They're not going to be continuous data, right? So one of the ways that you might consider adjusting for that is to actually kind of look at 25 as really being 24.5 to 25.5, not like a single number, or 75, 74.25, 75.5. So then you can kind of extend that to when you do your actual chi-square calculation. right? You can subtract that negative, that 0.5 from each one of your numbers that you're going to square, so that it becomes a smaller number to make it a more conservative calculation. That's called the Yates correction. Technically, you're really supposed to apply it anytime you have a 2x2 table. In reality, very frequently it's not used, okay, especially with a decent sample size. Right? So I'll leave it up to you guys to decide whether you want to use it or not use it. For our purposes right now, I would say to myself, if I'm doing some research later on and it's really a critical calculation, I'm going to employ the Yates correction because that's really right to do it. Right? Now, for our purposes though, I would just simplify your calculations and just do it without the Yates correction. Yates correction, also called the continuity correction. Get the idea? Correction for the fact that one variable is continuous, the other one isn't. Right. So I would, for your purposes, not use the Yates correction, but keep it in mind that it exists. One place you might consider applying it is, let's say that you were not to do this calculation and not use the Yates correction, and you got a chi-square value of 3.85. What would that tell you? That would tell you, it's so close that had I used the Yates correction, I might have failed to reject the null hypothesis. Maybe I should really consider using it. Did it make a difference here? No, right? Because look how big our chi-square value was. It was twice what we needed, right? So it's unlikely the Yates correction would have any impact on this in our calculation. But if it turns out to be really close, then maybe you want to go back and kind of consider it. Or at least mention that, mention in your results, I didn't apply the Yates correction, but maybe warranted because the outcome was so close. But that's how so it's pretty simple, right? I don't think that challenging. I'm going to move on to doing something else with these contingency tables, but then we'll come back and give you guys a chance to try this on your own, and also take a look at SPSS, using SPS to do this, because SPS will save you a lot of legwork in doing this as well. Okay, so I'm going to move on now, and I'm going to use the same table we just created. Okay. Okay, smokers, non-smokers, and cough, no cough. Smokers, non-smokers, cough, no cough. Okay, and this is expected, and this is observed. Okay, if I get it right against 25, 25, 75, 75, 100, 100. This was, I think we call this 35 and 65, 15, and 85. 100 smokers, 100 non-smokers. This was our observed values. This is what we expected. This top part doesn't really exist. It's just what we expected if there was no difference between the two. Okay, so now I'm going to take a look at this from another perspective. Okay, what's the rate of coughing in people? If I look at my expected value, what's the rate at which smokers cough? It's 25 out of 100. What's the rate at which non-smokers cough? Non-smokers, 25 out of 100 also, like 25 out of 100, right? So the probability of coughing, to be a cougher if you're a smoker, is 0.25. The probability if you're a non-smoker is also 0.25. Those are the relative risk, or in other words, the rate or the relative risk of coughing if you're a smoker or a non-smoker, right? So this is your risk of being a cougher if you're a smoker. This is your risk if you're a non-smoker. 25%, right? If you were one of those people in this group of 100. Okay, now I'm going to look at that as a ratio. I'm going to call that what's the difference in the risk here? I'm going to call the relative risk, relative usually means a ratio, a risk ratio. They also use the term risk ratio, as a matter of fact. What's the risk ratio between smokers and non-smokers? Well, it's 0.25 over 0.25, what's that equal to? 1, right? The relative risk of having a cough, smokers versus non-smokers, is 1. There's no difference, right? It's the same rate for both of them. Relative risk is equal to 1. I just do something there. Something happened there? Did I shrink? Yeah, how do I zoom back in? There we go. Okay. Yeah, same. It's just a different way of saying the same thing. Okay, let's do that right now with our real values, not our expected values, right? So what's it going to be for? So what's the risk for, what's the rate or risk for smokers? 35 out of 100, right? That's 30.35. Okay, so what's the risk for non-smokers? It's 15 out of 100 or 0.15. So what's the relative risk for smokers versus non-smokers? The relative risk is 0.35 over 0.15. And what is that? That is 2.3, if I'm not mistaken, right? 2.3. You're 2.3 times as likely to have a chronic cough if you're a smoker than if you're a non-smoker, right? So that's one way of looking at this, right? That's called relative risk. How did I do this? If I were to draw a box over here, and I put in this box the letter A, the letter B, the letter C, the letter D, the sum of these two is going to be A plus B. That was 100. Sum of these two is C plus D, right? So what was our relative risk? Our relative risk was A divided by A plus B over C divided by C plus D. Right? If you stumble, you don't remember, you might actually use that. But I think it's simple enough. You can just look at that and figure that out. That's relative risk. Another way of looking at this is odds. Anybody here play the ponies? It's such an old guy thing. Nobody goes, right? OTB went out of business. Nobody plays the ponies anymore. That's why they have slot machines at the track now. Nobody goes to actually see the jockeys and the horses and stuff like that anymore. Well, when you go to the track and they give you odds at the track, the way odds work is a little bit different. Okay, if I told you the odds on this horse were 2-1, right? Against, obviously, 2-1 against. Okay, what that is telling you that if the race was run 3 times, the horse would win once and lose twice, right? So if there's 3 outcomes, if there's 3 races, it would lose twice and win once. So the odds are 2-1. It'll pay off 2 for every dollar you bet. Okay, that's what odds are. Okay, if the odds are 20-1, if the race were run 20 times, you would expect that horse to win 20. If the race were run 21 times, you would expect that horse to win only once out of those 21 times. A little bit different than figuring out a prevalence or an association. That's how odds work. So if I look at this box, my observed values, what would be the odds of having a cough if you were a smoker? Well, the odds, if you're a smoker, is 35 over 65, right? The number of times out of 100 that you would have a cough over the number of times that you wouldn't have a cough. Number of times you would lose the race to the number of times you would win the race, right? A little bit different, a little less intuitive, right? But what are the odds for non-smokers of having a cough? 15 over, help me out here. 15 over what? 85, right? 15 over 85, right? So now let's figure this out. Now, what would we expect if there's no difference between being a smoker and a non-smoker, just like with relative risk? We would expect the odds ratio, right? When we divide the outcome of this by the outcome of this, we would expect that to be 1 if there's no difference, right? So what does it come out to in this case? The odds ratio comes out to 35 over 65 is how much? Point. Somebody calculate it for me. 0.538. I'm going to 0.54. divided by, what's the odds for a non-smoker? 15 over 85. 0.18. Okay, so what's the odds ratio? What's 0.54 divided by 0.18? It's 3, exactly 3, right? That's what happened. So the relative risk, you're 3 times as likely, 2 times as likely to have a cough if you're a smoker as opposed to a non-smoker. I got that from relative risk. The odds that you have a cough if you're a smoker versus a non-smoker is 3 times the odds. Both of those are measures of how risky is smoking in terms of like having a chronic cough. They're both measures that are used, pretty commonly. Yes.
Okay, but when especially for odds, you did it like 2 to 1.
Yeah.
And then if the odds ratio is 3, then it's 3 to 1.
No, it would mean the odds. No, it's odds ratio. It's not the same thing as odds. It's just the comparison of the odds of a smoker to the odds of a non-smoker.
But
So
it's not times that.
no, not really. Yeah. Well, the odds are 3
What
times
does
as
that
likely.
say? We can't see it. If it's where
Oh, excuse me. Let's get that out of the way. You want to know something? It'd be easier for me to do it here. Yeah, it's not quite the same. It's not quite as direct.
the odds you have a copy of
The odds, no, the odds that you have a cough if you're a smoker is 0.54. The odds that you have of having a cough if you're a non-smoker versus is 0.18. Okay. The 3 is the odds ratio. Okay. In other words, the odds of having the odds of having a cough if you're a smoker are 3 times the odds of having a cough if you're a non-smoker. Right? Because that's fraction. That's what fraction actually describes. Yes. I'm sorry, a little louder. Risk ratio and odds ratio. Okay, well, the risk ratio is based on the number of people that have the cough over the total number of people, right? It's kind of a rate. It's kind of like a prevalence of disease, right? It's a rate, very easily understood. And we do it for smokers, we do it for non-smokers, then we divide one by the other to see how different they are. Might have been only 1.1, might have been 1.2, right? The bigger the difference is, the more encouraged we are that it's real, not due to chance. The odds ratio, odds are represented differently. In other words, if you test, if you were to say, if you were to, trying to think of, if you were to roll a dice, right? Yeah, it's like in other words, there's 6 possible outcomes if you roll a dice, 1 through 6, right? The risk of coming up with a 1 is 1 out of 6, 1 out of the total. The odds of coming up with a 1 is 1 over 5, because it's the number of times you get the outcome over the number of times you don't get the outcome. Like at the track, the odds of 4 to 1 means that the expectation is if you ran the race 5 times, you'd lose 4 times. Yes?
So just to clarify the number 3, and it's technically, since it's a ratio, it's 3 over 1.
Yeah, it's unitless, has no units, right? Because it's a ratio. Go ahead, yeah.
So for every 1 non-smoker who has a cough,
I wouldn't apply it that way. I would just say that you have 3 times the odds, kind of the likelihood.
so
Why would you use one over the other?
what you were saying with the track, like if you race, I'm 21 races.
Yeah.
So what equation would that be?
That would be, okay, no, you got a good idea. Let's take a look at that. If I were to lay this out the way I did the other one with that my A, B, C table, What would that look like? That would look like, instead of A over A plus B and C over C plus D as being my relative risk, right? What is it going to be now? My odds ratio is going to be equal to A over B divided by C over D, right? When I say 3, it's the odds ratio. It's the ratio between the odds for smokers versus the and to have a cough, and the odds for non-smokers to have a cough. It's the ratio between the two of them. Yeah, that's true. Oh yeah, yes, you could say that. Yes. Okay. In fact, if you try and do it with chi-square, you're gonna have a problem. Don't let you do it unless it's 2 by 2 table. When you try and we're gonna try it with SPSS to see how that works. Okay, so now if I came up and told you the relative risk was 1.1 and the odds ratio was 1.2, would that you encourage you to say that there's an association between smoking and non-smoking? Probably not, right? You'd say to yourself, well, the perfect outcome will be 1, but I can't expect the perfect outcome in a real study. So I wouldn't be surprised to have a relative risk of zero point 0.9 or 1.1 or something like that, a little bit different than that, right? Because in a real study, things happen. One group is going to be underestimated, another group might be overestimated, just a little bit, right? But if you got a relative risk of 7, that this group was 7 times as likely to have lung cancer as the other group was, well, that's pretty dramatic. You wouldn't expect that to be wrong. There's a problem with that. You can't really quantify that very well, can you? It's a big number, but how can I be sure? What's the probability that I would get that big a number and be wrong if I said that there is an association between, say, smoking and lung cancer in that case, right? I can't depend on that. I need to quantify that. So when we had a proportion, one of the ways that we figured out, or mean, one of the ways that we figured out how accurately we had determined what the mean was, or what the range of real means or real relative risk. So we're really interested in what's a real relative risk for the entire population, not just for the 200 people we sampled. What's the odds ratio for the real population, not just the 200 that we sampled. Okay, so now what we really need is we need a confidence interval, right? So if we can determine a confidence interval for relative risk or for odds ratio, we can tell whether or not we can reject the null hypothesis. Let's say I told you that the odds rate, that the confidence interval for the relative risk, in this case it was 2.3, right, was a relative risk. What if I told you that the confidence interval, 95% confidence interval for the relative risk of 2.3 is 0.8 to 4.2? Would you reject the null hypothesis? Yes or no? How many of you guys think yes? If I told you that the confidence interval for my result for my relative risk is, my result was 2.3, but the confidence interval is 0.8 to 4.2. Well, what we're saying is that there is a chance within my 95% confidence interval, there's 5% chance, or there is a chance within that confidence interval that it could be 1. But what does it tell you if it's 1? The population relative risk. It tells you there's no difference between the two groups, right? Now, if I had told you that the relative risk was 2.3 and the confidence interval for that value was 1.5 to 3.5, would you reject now? And the answer to that is yes, you would reject, because you're 95% sure it's not 1. It's greater than 1, right? So that confidence interval, the relative risk, the odds ratio, they give you the magnitude of the difference in your observed values to your expected values. The confidence interval for the relative risk or for the odds ratio, they give you the justification for rejecting the null hypothesis. Because if you can say with 95% confidence that the risk is more than 1, relative risk is more than 1 with 95% confidence, then you can say, well, the risk of it being 1 is less than 5%. The chances that it is 1 is less than 5%. So there's only less than 5% chance you'd be wrong if you say there's an association, reject the null hypothesis. Okay? So I see a lot of slightly confused faces, not terribly confused, slightly confused. Really shouldn't be that confused because it's really more straight. I have the feeling that you're reading more into this than there really is. That somehow in the back of your head you're saying to yourself, can't be that simple. What I'm looking at can't be what it really is. That you just divide this box by this box and come out with this number. But trust me, that's what it is. The hard part is calculating the confidence interval. And how do you calculate the confidence interval? Well, for your purposes, we're going to use software to do that. Okay. Now you could calculate it because what are we dealing with here? We're dealing with proportions, and we know that there's ways to calculate what the standard error would be, the distribution for proportions, standard error, find what the p-value is, which might be 0.35 and the other might be 1, and figure out what the confidence interval would be. There are ways for us to figure that out. We have a vague idea in the back of our heads for when we were doing confidence intervals with proportions. A little bit more complicated here because we got 2 proportions, or we have 4 proportions that we're dealing with, 0.35, 0.15, 0.54, 0.18, right? But we're going to use software to do it, okay? So let's take an example. Okay, so now one of the documents, let me look online here. Anybody? I'm sorry. I think he's reject. Thank you, Brian. Somebody online is still awake? Thank you. Okay. So what do we have here? We have